Log on, tune in, find out. Another good idea from Cambridge.
Experimental design for systems described by partial differential equations. Many years ago, when I was a PhD student, my supervisor gave me several papers and a book written by Ewaryst Rafajlowicz. I didn't understand anything at that time, but as years passed, I started getting some feeling. I tried to follow it, but now I'm sure that we deal with someone whose insight and erudition I admire. I hope you will do the same. So I present you Ewaryst Rafajlowicz from Wroclaw University of Technology.
Many thanks, Professor Ruciński. Mr. Chairman, ladies and gentlemen, I would like to present some results on input signals for parameter estimation in the so-called distributed parameter systems. That is systems for which space and time variables are important. Really, it was about 30 years ago when I started digging in these fields. And from that time I collected several results, but only recently, due to being invited here, I was able to prove some results which are in some sense conclusive. So I would like to show them at this presentation. So once again, thanks for opportunity to being here. And my presentation starts again from systems with only time dynamics, but in opposite to today's presentations, it will be on systems with the so-called continuous time, described by usual ordinary differential equations instead of difference equations. And this is introduction and the building block for what we are going to show later. And then I will show some results for distributed parameter systems and describe special cases for which characterization of input signals in space and frequency domain are in some sense complete. As I said, our introduction is on linear time invariant dynamic system. Then we discuss briefly generalization this approach to unbounded power input signals. Then we focus on systems with space and time temporal dynamics, also known as distributed parameter systems. We shall try to illustrate interplay between space and frequency domain structure of input signal and indicate that new technologies in sensing and actuating such systems can lead to new and sometimes even easier problems for input signal selection. In order to get something more than numerical algorithms and simulations, we impose some constraints. We confine to a class of systems which are described by a certain subclass of partial differential equations. Observations are assumed to be made continuously in time. The theory conveys to discrete sampling, but the formulas are less transparent. Of course, we, for simplicity, assume that observations are uncorrelated in space and time. We do not allow feedback between output and input of our system. Thus, this means that we are interested in precise estimation of parameters of partial differential equations. Why? Because partial differential equations are useful in many fields of engineering, in heat conduction, diffusion, chemical engineering, and many other fields. And we would like to know what precisely parameters are in this specific installation that I have to identify and to control later. So, closed-loop experiments are excluded from my considerations. For simplicity, we also assume that we have a long horizon of observations. Let's look briefly for the history of parameter estimation in systems described by partial differential equations. As early as in 80s, Kitamura considered minimal requirements of identifiability of parameters. Then there was a stream of papers on how to make easier parameter estimation by clever selecting sensors movements or input signals. For example, in one of my old papers, there was an attempt to put sensors along characteristic curve of partial differential equations, which reduces the problem to ordinary differential equations. But of course, our main emphasis will be on optimization of achievable accuracy of parameter estimation. Names of Mera, Laniotis, Goodwin, Payne, and Zarop appeared today in earlier presentations. Why frequency domain approach? Because in the frequency domain, we are almost in the same framework as in the spirit of Kiefer-Wolfowitz theorem for optimum design for regression estimation. To illustrate this briefly, consider a linear time invariant ordinary differential equation. Its solution depends on vector of unknown parameters bar A. Assuming that available observations with additive noise are available, then we can obtain the following information matrix. As usual, we have sensitivity vectors of solutions of differential equations, and from Kramer-Rao inequality we know that it is reasonable to minimize the determinant of inverse of Fisher information matrix. What is the difficulty with these problems? If we express information matrix in full details, then we will have the following difficulties. Namely, here we have input signal in different times, and this is non-convex. This is the same difficulty as today's morning Professor Pronzato mentioned in his presentation, mathematically the same. And how it is overcome in frequency domain approach. Namely, assuming large observation interval, we can replace this multiplicative structure by autocorrelation function of input signal. So the averaged information matrix looks much nicer, and it can be expressed even better in the frequency domain using the Parseval theorem. We can have such a structure which is quite similar to that what we are getting in Kiefer-Wolfowitz setting for regression estimation. SU of omega is spectral density of input signal, and this is Fourier transform of impulse response sensitivity to parameter changes. The clue from this is that information matrix is linear with respect to spectral density, and it is in fact the spectral density which in general can be complex valued. Here it is real valued because of symmetry of autocorrelation. Now, assuming that we have bounded energy of input signals, we can express bounds for input signals as integrals of spectral density, and we assume, of course, that above certain frequency we cannot generate input signals because it can be too difficult or too dangerous for the system. The set of all admissible spectral densities is convex, and it is important special case were to be considered, namely sinusoidal inputs which are represented in frequency domain as spikes of Dirac delta functions. Frequency 0 is interpreted as constant signal. And clearly spectral stripes of mixtures of trigonometric functions are located at omega 1, omega 2, and so on. Just consider a simple example how it works. We have a simple system with one unknown parameter. Its sensitivity to changes of this parameter is given by this equation, and in frequency domain as here. And it is easy to see that the best what we can do is to use frequency 0, that is constant signal, as the optimal input. In more generally, we can state the problem of the optimal design of spectral density of input signal. Here and later we concentrate on the optimality, but all the results easily convey to linear optimality criterions and to the so-called LP class of criterions. Of course, we have the same difficulties as always with nonlinear parametrization, some kind of course of a priori knowledge, which is usually overcome by using either nominal parameter values or worst case or Bayesian approach, or adaptive approach and something like that. Later, for simplicity, we use nominal parameter values, but results are also relevant to Bayesian approach. Under these conditions, we have the following result, which is from 70s, that the set of all achievable information matrices is convex, closed, and bounded. So there exists unique information matrix which solves our problem, but it can be achieved by different spectral densities. And every spectral density can have his discrete counterpart, which contains at most a given number of sinusoidal components with the same information matrix. So the problem, which is at the beginning intractable, is reduced to the known problem of finding frequencies of sinusoidal inputs and their amplitudes. And the counterpart of the equivalence theorem is also true. Maximum of prediction variance should be equal to the number of estimated parameters. And at every support point, we have equality. Or maybe condition condition 15, this one, allows to check the optimality of a given spectral density, but if we do not have an idea how it can look like, then we can use slightly modified version of algorithm, well-known algorithm of Professor Wynn and Fedorov. Just to be sure that this is not so difficult, we can consider, let's say, estimation of two parameters, this one and that one, and we can prove precisely, not numerically, that this input signal is optimal in this case, just calculating elements of the Fisher information matrix and proving that maximum is attained in this case, which is equal to. And optimal frequency is equal to one of an unknown parameters here. For different values of these parameters, this maximum is of course attained at different locations. And how much do we lose if instead of optimal frequency we use frequency which is slightly different? The curve of efficiency is shown here. If our misspecification is less than about 40%, then efficiency is larger than 80%. So we can, even without being very precise, we can gain a lot using frequency from surrounding of the one which is optimal. All the above can be conveyed to when we extend input signals to the class which is allowed to grow faster than bounded sinusoids. Namely, we can allow signals which behaves like that. And then the optimal input signals have the form that it is monomial in time multiplied by linear combinations of sinusoids. This generalization was published in my paper in '84. And of course its usefulness depends on whether we can allow to treat our system with such quickly growing signals. Now let's turn to our main topic, namely distributed parameter systems. In '60s, when this theory started, a main paradigm was that observations can be made only in selected spatial locations, and also actuating of such systems is possible in finite number of locations. But after 50 years, we have quite new technological achievements which like usual cameras, infrared cameras, which provide information with let's say 10 million points from a given piece of our system. So we can assume that we have in our disposal measurements at every point in space. Let's look at the example. This is infrared image of wall of heating furnace, which is used for heating large enterprises or supermarkets and so on. And we can precisely say where the largest temperature is located, when the smallest temperature is located, and so on. Other devices which emerge in the meantime include optical devices for observing strange fields, three-dimensional laser scanners, moving and mobile sensors, the so-called MEMS. We can also estimate velocity fields from sequence of images. On the other hand, we have new possibilities of forcing, actuating our systems. These include high energy lasers, which can be treated as moving sources, microwave heating inside quite large three-dimensional bodies, shape-changing materials, which can act as forces distributed in space. In conclusion, we can look at the theory under new angle, trying to consider theory for spatial spread observations and forcing in space. In general, linear distributed parameter system can be described by its green function, which is denoted by G capital here, input signal, and this is state of our system at point x and time t. When we assume input signals acting on the boundary or pointwise sources, then the results are similar to that for ordinary differential equations. But if we allow spatially distributed sources and observations, then the theory becomes quite nice. We do not need green function explicitly. We can calculate it sometimes numerically, but we concentrate on the case when this green function is known as in terms of eigenfunctions of a spatial operator. Before stating the problem, let's look for a simple example of heat conduction equation. Here we have one unknown parameter, and the Green's function looks very familiar. If we put a source at 0, let's say, a heating source at 0, then the optimum sensor trajectory is shown by this curve, square root of time. But if we allow moving sources and moving actuators, then it occurs that the best way is that sensor follow moving source. What does it mean? In fact, we should consider jointly input selection and sensing, and also rate of sampling. But it is too difficult. It is not non-convex problem, and we concentrate on problems where sensors are located, and we would like to choose input signals only. It is possible to obtain general results in terms of green function operator, but these results are not so constructive as those that I'm going to show you. Consider the following class of linear time invariant systems. Q is again system state, A of x is spatial differential operator, and if this second derivative is present, we have systems of hyperbolic type like wave equation or vibrations of strings, plates, and so on. If this term is not present, then the rest is a parabolic type equation which describes heat conduction, diffusion, and so on. Here we have examples of such elliptic operators which should be accomplished by boundary conditions. More generally, we meet operators of the following form, which are symmetric, positive definite, and we assume that eigenfunctions do not depend on known parameters. This happens if these eigenfunctions are eigenfunctions of each separate operator in our general description, if V is eigenfunction of each of them. Under this assumption, plus assumption that V form complete and orthonormal basis of L squared functions, we can express green function as follows: as a linear combinations of eigenfunctions and impulse responses for each mode. It is in engineering term for eigenfunction in space. This is in engineering. This is called modal decomposition of distributed parameter system. Assuming as earlier that our input signals are act in space and time, and introducing autocorrelation function, but note that this time it depends on both on two positions where our U acts on our system, we can express the Fisher information matrix as follows. It looks very complicated. Our constraints on admissible inputs are of the form, and they are interpreted in terms of energies again. Again, we have that the class of all admissible attainable Fisher information matrix is convex, closed, and bounded. And we can express information matrix in more manageable way, like this. And these are spectral densities for each eigenfunction, for each spatial mode. Constraints translates also to manageable case, and we can prove the equivalence theorem that optimal input signal is the form which is shown by 29, and it is de-optimal if and only if the following expression attains its maximum with respect to frequency and with respect to spectral number in space, which is equal to number of unknown parameters. Recall that under our assumptions, eigenvalues are linear functions on unknown parameters. So we can calculate all of this precisely. For hyperbolic case, for parabolic case, we have sensitivity in frequency domain for each mode like this, and for hyperbolic case it looks like this. It's known expression for oscillator, but relevant to each mode in space. Thus, after these calculations, we can express the equivalence condition, the equivalence theorem like this. We can split finding optimal frequencies and maximum with respect to spatial modes. Summarizing this part of results, we can say that optimum input signal have the following form. It consists of it is a finite sum of single spatial modes multiplied by single waves, sinusoidal waves. And what has to be established is amplitudes of these sinusoidal waves. This can be done by solving usual optimum experimental design problem, in the sense that we have unknown weights here and known vectors bk multiplied by multipliers dependent only on frequencies. And this is well-known problem, and it can be solved numerically if necessary, but in some cases it can be even solved analytically, as I will show later. Summarizing the procedure of finding optimum spectral density is as follows. Find the best frequency of excitation of each mode, which is here. Calculate vectors bk, which is easy when we know structure of differential operator. Solve the problem, this auxiliary problem, like this, and form optimum input signal, which consists of spatial modes multiplied by sinusoids. Theta, this phase shift is can be random. This is the standard, the optimal experimental design problem. We reduced our problem to the one of, and we can calculate weights sigma 1, sigma 2, and so on using either multiplicative weight updates in the version of Torsney and Fellman, or if we have a very large number of modes to be taken into account, then we can use exchange algorithm of Wynne and Fedorov. One can ask why we consider only first R and eigenfunctions instead of trying to select eigenfunctions which are better. In fact, eigenvalues of typical systems drop very fastly to zero, grows very fastly to infinity. So this in frequency domain, this translates as very fast decreasing to zero of these multipliers. And what if we do not know our eigenfunctions, modes of our system? We can calculate them numerically, even in very strange domains. Let's consider the following strange domain, like this, and try to calculate eigenfunctions of an elliptic operator. Using available software, the first mode looks like this, the second and third mode looks like this. So even in very strange situations we can find how this mode looks like. Now let us be more specific. When we consider parabolic systems, that means heat equation or diffusion equation, then we can prove that in fact optimal input signal is constant in time. Only its shape is important for better estimation of parameters. And if our eigenfunctions do not depend on unknown parameters, then also this input signal does not depend explicitly on unknown parameters. Maybe in some cases only this sigma case may depend, but there are different situations. The second corollary is that if our system is of the hyperbolic type, that is, we consider vibration of plates, strings, and so on, then optimal frequencies are of the following form. So in this time, optimal input signal is consists of spatial mode multiplied by sinusoidal excitation with frequency which depends on the number of this mode. And of course eigenfunctions depend on type of boundary conditions and the shape of the set where our system lives. Let's look in the hyperbolic case how complicated can be our input signal in space and time. Here we have space variable and here we have time variable. Isn't it possible to generate such signal and apply to our system? It's quite other question. For us it is important that that is some kind of lower bound. We cannot get better results in the sense that if we allow to spatially continuous measurements, spatially continuous excitations, then we can obtain this and this quality. And if we have to impose constraints on outputs or inputs and so on, then we cannot get better quality than signals, than provide signals like this. One can say, but I don't know how this frequency looks like. Because it depends on unknown parameters here. But fortunately, even if damping is relatively large, we can say, I don't know which is good frequency, but this is resonant frequency. So shake your system in this way that each mode obtains its resonant frequency. For parabolic case, we have a somewhat better situation. As I told you, optimum input signal is constant in time, so we have to bother only about shape in space. And this shape depends on boundary conditions. Here I have shown some examples how it can look like for boundary conditions of the first, second and third time kind. All the above results conveys to the cases when our elliptic operator has multiple eigenvalues. Also to L and LP optimality criterions. The equivalence theorem looks similarly, although maybe results are not so conclusive as I shown for the optimality criterion. Part of the above results can be generalized also to systems with specially varying coefficients. But note, of course, not these results that I shown at the end. What is left outside of this lecture? Time domain synthesis of input signals when we have finite observation horizon. Some hints on solving these problems are shown in my paper from '89. But at the Vienna conference I'm going to present more conclusive results also for time domain synthesis in the spirit close to the one shown here. Selection of sensors positions, trajectories of moving sensors are almost solved. Many valuable results are collected and obtained and collected by Professor Uciński in his monograph. Open problem is simultaneous selection of sensors, positions and input signals. What is also left outside this presentation? Sampling rate optimization, also closed loop experiments. Since it is known from old times, these are results of Söderström, Ljung and Gustafsson. Then when we have not input power constraints but output power constraints, then feedback can be beneficial for experiment. In conclusions, I would like to say that under many simplifying assumptions, it is possible to say that optimal input signals are products of natural modes of the system, and time excitation for each mode. Should we apply these results in practice? Not necessary, because we have no free space for testing whether our model is adequate. So I would advise to use mixture of, let's say, these frequencies and other frequencies which are not taken account and possibly important for our system. We have just a moment. We have a long bibliography here, but I would like to show you one figure also, which is in some sense illustrates why not to use these designs without critical point of view. We have a hanging bridge, and optimal input signal to ask him about his parameter is to shake it in this way, that this is force in space and here is force in time at resonance frequency. And what we have after the experiment. Thank you for your attention.
Open discussion.
One thing I've never quite understood: if to possess a resonant frequency, you surely need feedback. In other words, if you have this ordinary differential equation like simple harmonic motion, that's feedback, and that has a resonant frequency. So I can't understand. So at some stage you in your talk you started without feedback, and then later on, since you talked about resonant frequencies, you started to have feedback. Is that right?
Let's say, for the theory to be clear, the answer is use resonant frequencies, whatever you can generate them. And for practical applications, if you don't know what is the resonant frequency, then try to find it experimentally. And then you, of course, you use feedback. But we have clear theory and slide about one slide about how to cope with this without knowing unknown parameters. But theory is proved without feedback. But the conclusion is generate resonant frequencies. How? It's outside this theory. Okay.
Yeah, I wanted to say that maybe in the cases where you don't have a simple geometry, so in this, like these two ovals that you had overlapping, computational effort of computing the eigenmodes is probably higher than if you just solve the problem directly numerically.
Yes, the problem is directly numerical, but it is this is shown that it's not difficult in many cases, at least in two space dimensions. Maybe in 3 dimensions it can be more difficult. But in fact, what we need, because eigenvalues grows very fastly, and this means that eigenmodes influence drops very quickly. So in fact, in practice, it suffices to excite 2-3 modes, and 2-3 modes we can calculate for even complicated geometries. Is it answer to your question, or?
Yeah, what I wonder is if you just discretize the control using finite element basis, and solve directly the problem.
It is discretized in the sense for computations. Results, we have, let's say, pure and nice theoretical results if we know eigenmodes. And if not, then use something which approximates an eigenmodes.
But it strongly depends on the type of equation. If you have equations from computational fluid dynamics, so the number of nodes can be several millions.
Yeah, of course, but let us know that these conclusive results were for easy partial differential equation, for easy classes, namely for parabolic equations, and if hyperbolic, then only second order. This class does not include equations, transport equations like fluid dynamics, which are hyperbolic, but usually much more equations is needed to describe the phenomena. So it is outside.
I mean, earlier in the week we had some equations, differential equations, which didn't have constant coefficients. For example, had polynomial coefficients. Do you have any insight? Because these are very important class of, I mean, the solution of such equations leads to nearly every special function in physics. So, do you have any when you integrate, you get parameters when you integrate. So, do you have any idea, any handle on differential equations with polynomial coefficients?
You mean input signals for
Yes.
such?
No, for the actual differential equation.
Yeah, this what I said to some extent conveys to specially varying coefficients, let's say polynomials, but not this last part. Only general equivalence theorem conveys in the sense that I can write integral equation with eigenvalues and eigenfunctions. I can say if eigenvalues and eigenfunctions fulfill this, then that it's okay. I have and then we can use your algorithm with later improvements just to calculate for a given example how it should look like for a specific case. But no conclusive results like this, that for constant parameters I can split modes in time and space. Thank you for this question.
Francesco.
Thank you. I have a question regarding the point 4 in your conclusion, so model consistency. And so you suggested to use new frequencies, but could you suggest other tests, say Hilbert transform using a Kramers-Kronig relation, or something that could be useful, say, for experimentalists?
But what kind of test do you mean? Because
Just to test whether the model is correct, given that you have a certain set of data.
All the theory goes when we assume that model is correct. Then we can prove all
So
nice results. But
point 4.
But if this is as in let's say the optimal design for linear regression. If you assume that your regression is linear, then you have observations +1, -1, and no chance to test linearity. And if we allow that our theory is not, our equation is not a good model, then, as I suggested at conclusions, it is better to use mixture of these good frequencies and some, let's say, spread in frequency signals, in frequency and in space, in order to be able to test. But let's say, if you in 90% believe in your model, then use only 10% of energy to leave for testing. If you believe in your model in 50%, then of course, even maybe it is better not to use this. Just use white noise in space and time.
So So if you're interested in sensor selection for model discrimination, so we have some results with my former PhD student Bartosz Kuczewski, who tragically died last year. So he has written a book about this, so we can discuss it.
Okay, we'll discuss it later. Yeah.
My impression is that you strongly use Green's functions. If you reformulate this a little bit using the formats of strong and continuous semigroups, which is almost dominated the control community in this area, the results would be much more accessible and of even bigger interest, I think.
Thank
So
you for this.
It seems to be easy to
Thank you for this suggestion. So, of course, it is possible to formulate all of this in terms of not in terms of Green's function, which is very easy to understand. I just put plate here and deflection is here and so on. But this way of presenting results will be probably better publishable. Thank you.
Any questions? So thank you, our speaker, once again.
Thank you. Welcome.